So my name is Markus Gerber. As already introduced, I'm Senior Business Development Manager in an area we call Data Solution. But first, nVent Data Solution. So nVent is a US-based or US company. We are listed at the New York Stock Exchange. We are about 3 billion total global sales. And from this picture, you can see we are active in different verticals, while data centers is by far the fast growing vertical we have. So just giving a brief introduction to the company, and now let's get to the topics. But before jumping on the different cooling solutions, I also summarized something around ESG. And at least I got confirmation from the previous session that this is exactly the topics we talk to. Of course, we as a global company, as a corporate structure, we also have our own ESG reporting and report outs. That's an important thing, being sustainable. But there are challenges, and we will have a look at that. So first of all, I'm a big fan of the Uptime Institute on their annual survey. So at one point, I think I need to get something back on promotion I do for them. Nevertheless, what you can see is the average PUE, and they do this. It's around 600, 700 data centers globally, and you can see it massively dropped since 2007 to 2014. And one major reason is that, and I remember I was already around that time, that this was starting to look at improving data centers, making them more efficient, and also introducing aisle containment systems, air management systems. But we will have a look. So that's one benchmark we can see, and also we can see the challenge that will come to further improve it. And in parallel, we talked a little bit about the European directive. I think it's an important point. So there is a web link in my presentation if someone wants to read it. There is a lot of movement around. Where I struggle, and I agree, yes, we all have to contribute to it, but the main focused area in the directive, if you really open it up and read it, is first transportation, which consumes a little bit more than 30% of the energy at the moment. Then poorly isolated buildings. So building is also a second area. And surprisingly, third, with 2.7 or 2.8% of the energy consumption is data centers. So even it's a small portion, it gets a large space in the directive. And because Germany is a little bit behind by getting more energy efficient and have a bad ranking, they stepped ahead, and they think it's the first country defining a country law, which looks at the PUE measurement and also at the energy reuse factor. And data centers at a certain size, there's a difference between governmental and privately or company-owned data centers. They are obliged to fulfill and provide measurements, and this will happen in several steps. So this is giving the framework. This is one framework. Now you could say, why should I care about Germany? Why should I care about Europe when I'm based out of the UK? Also, this is broken down in several countries, which will work on those. And also in the UK, you have this zoning policy on heat reuse, and you have the energy performance certificates, which also includes data centers. So governmental impact on data centers is one driver. And then, of course, sustainability is another driver. And then the last thing, and we have heard this also during the panel discussion, is new demanding applications. And I just pulled some examples out of the news. I think it's just to underline that liquid cooling, higher densities from a technical point of view, and an appetite on those applications will come. So we got these three different areas that drive the market. Now, let's get into data center and the data center way of cooling. I already mentioned the massive drop on the PUE came from the air management from aisle containment. So what I pulled together here is just a comparison, very high level comparison. And let's walk through on the design, left-hand side, you can see, and then design. We are now getting from a room-based aisle containment crack unit design to aisle in-row cooling down to the server. So we are moving closer to where the heat is coming from. Secondly, the approach. So we have heard air. Yes, we are moving from air, and we would call it indirect water cooled with a rear door solution to direct water cooled. So we are changing the cooling medium. In parallel, we also increase the density of the cooling solution, as air clearly has limitations. Of course, you can build an aisle containment with, I don't know, 20 or 30 kilowatts or chimney systems, but I would question if it still makes sense to move such an amount of air. And therefore, I would say there are clearly limitations, and that drives also towards different cooling solutions. And then inlet temperature on the fluid side, on the water side, the more we move to the right, the higher inlet temperatures we can implement, and the more we can use free cooling, the less energy we need to cool down the data center. And then, of course, we heard this also before, the energy reuse. I know that the new chiller systems, also in an aisle containment, they are quite efficient, but we are getting towards liquid. We can transport the heat better, and we can also drive with higher inlet temperatures. We can also drive towards higher return temperatures. And then the last thing to mention, and we will have a look during the presentation, is clearly the risk. So we are running through a shift in the industry. So when we talk containment, in-row cooling, this is well-known layouts, well-known design, air-based cooling, so everyone knows how to plan and operate a data center. The more we move to the right-hand side, the more challenging it becomes, because people don't have the experience here. And another thing is, we have to see that the compute and the infrastructure kind of merge together. So the cold plate is part of the server. So we are not in a position anymore where we say, let's build an air-cooled data center with 19-inch racks, and we pull in whatever 19-inch server we have. We look at the number plate and we say, okay, this server has to operate with this certain temperature, so let's put our SLA on the data center around the temperature. No, now we are getting into the server, or even immersing servers. So that's just an overview on the cooling solutions. And what I want to do today is getting a little bit deeper into rear door and, of course, direct to chip and immersion. So, as I said, we are moving from one solution, or there is a change to a new solution. So what we did is we compared an in-row cooling with a rear door cooling. And people sometimes say, yes, the investment is higher. Yes, we are talking a rack-based cooling solution against a raw-based cooling solution. So the time you need less in-rows, of course, your invest and also your OPEX for maintenance and all the stuff will be lower. Another advantage on the rear door side is you can keep the length of your aisle, while on the in-row you would need more space. But we will also come to that. So our conclusion here is, if you have a load lower than 15 kilowatt and your water supply is also lower 18 degrees, then the in-row might be a good choice. If you are challenged and you have higher loads per rack and you want to increase your water supply temperature, then the rear door comes in place. So let's take a simple comparison or a use case here. So what we did is we said first cases, 200 kilowatt installation. We are planning 10 kilowatt each rack. What we have to do is we have to fix, to compare the both cases, we fixed airflows and fluid flows. And we said in the first scenario, we have 14 degrees facility chilled water. We operate at 35 degrees exhaust air temperature. And then we would come to the layout in the bottom where we say traditionally aisle containment using in-row coolers, in that case, 8 in-row coolers with a capacity and reserves for redundancy of close to 250 kilowatt, with quite reasonable temperature ratings. If we do the same with the rear doors, we would have a massive higher amount on rear doors. We would, of course, exceed the cooling capacity, so we would run only on the low performance with the doors. And I think the only advantage or the only consideration to go with a rear door in such a case is you want to have capacities for future growth, or you really need to save this little space on your footprint, which is around 4 square meters, because what you see here, the small squares, is floor tiles, 600 by 600, while 800 wide racks and 1,200 deep. Now let's move to the second case. We still keep the same overall density, the overall load, but now we put 20 kilowatt in each rack. We keep the airflow, we keep the fluid flow, but what we also do is we increase the inlet temperature on the chilled water side from 14 to 24 degrees, and we accept a higher exhaust air temperature on 40 degrees. Now looking at the same layout, we would of course need significant less space, but by reason of redundancy, we would need a massive higher amount or quantity of rear doors, while also looking at the given values, we would almost operate at 30 degrees cold air. And I think that's not really feasible. Then when we take this with the rear doors, with the rear door cooling units, we can cover it rack-based 10 units. We still have capacity reserves. We need much less footprint, and there is no problem to operate in this temperature range because we got the 40, we got lower than 26 degrees on the cold air side. And that was just an example comparison how the in-row versus the rear door would work. So in summary, aisle containment, in-row cooling still makes sense if you accept to have a limited load per rack. The time, okay, I have to be prepared. The density will increase. I also want to drive on higher water temperatures, then step to the next level on indirect liquid cooled rear door solutions. And now let's boost the door a little bit, because what we can do here, of course, is we can work on flows. So the first example, and I just pulled a couple of calculations in here. The first example is getting kind of maximum out. So this is 86 kilowatt per rack with a rear door, and of course with high flow rates on liquid and air. Nevertheless, it's possible to do it. If it makes sense is another question. And then what we did is we took the same exhaust air temperature and we step by step increased the liquid temperature by keeping airflow and fluid flow on a constant level. And then, of course, you see from 14 to 20 to 24, the cooling performance drops while it's still in a feasible range. And I think we are not going from 10 to 55 kilowatt per rack by tomorrow. Therefore, if we again fine-tune the airflow and the fluid flow, keeping the 24, 45 air and fluid inlet temperature, we would be in a range of 42 kilowatt cooling capacity, meeting a delta T on the fluid side of 10, slightly higher than 10 Kelvin. This means we go in with 24 degrees, 34 return, which is a good starting point for heat reuse, as you see on the left-hand side. This means long time a year free cooling, efficiency data center operation, and high temperature out, which could be used in heating homes, heating swimming pools, farming, whatever plants. So I think that's another advantage we have with the rear door. And of course, this playing around with the operating conditions, the door is regulating itself. So especially on the airflow, we are using a differential pressure sensor, which only makes the fan turning if the equipment is not powerful enough to overcome the pressure drop of the coil. By doing it or regulating in that way, we also reduce the power consumption of the doors to a minimum when there is no load. Otherwise, we use PD controls, meaning we get a set point in, we measure constantly the operating conditions, and then we regulate against that point. So very advanced regulation, and then of course interfaces to monitor and report out any data on the cooling side. Let's go to the next step. Just have to look at the timing. Okay, so I have to speed up a little bit. This is the direct water-cooled main architectures. While I would say, don't read the small boxes. This is more for me to keep the definitions in front of my eyes. But in a nutshell, what we have is cold plate cooling and then immersion cooling using two different types of liquids. Single phase means it's stable. It's not changing its status like water. We are not boiling water in the data center, so it's just getting warmer. Or it evaporates. That's a two-phase cooling media. And what we are looking as a company is the cold plate cooling single phase using water over water glycol mix, and the liquid immersion cooling on a chassis level. So precision chassis level immersion cooling, also using a single phase liquid here. And how would it work? Very generic. I'm starting from middle right to left. So you have the IT equipment that's mentioned with an inbuilt cold plate or a chassis with an inbuilt server. You connect this to a manifold on the rear side of the rack, so similar to a PDU. And there, through the manifold, it flows liquid through the cold plate. And that's what we call the secondary circuit. And this liquid flow is provided by the cooling distribution unit, CDU, with inbuilt pumps. Within the CDU, you have a liquid-to-liquid heat exchanger, and the CDU is then connected to the facility circuit. This means we have two liquid circuits separated from each other. We are getting flow and chilled water from the facility into the CDU, while the CDU pumps the liquid through the cold plates or through the heat exchanger of the chassis, and the heat is transferred in the CDU back to the facility. Just to mention, and we have heard this before, cold plate cooling still requires complementary air cooling, as the cold plate is not capturing 100% of the heat with liquid. On the chassis immersion side, we don't need complementary air cooling, while we would need the chassis and the integration of the server into the chassis, but we are getting close to 100% liquid cooling. The only heat is due to radiation of the racks into the room. Briefly on the design options of the different CDUs. So there is a rack mount CDU. The rack mount CDU is built for building really a system within one rack or two racks, supporting the manifolds. So a smaller area in the data center supporting cold plate or immersion cooled equipment. Then if you scale, there is a standalone CDU, which supports several racks. So just giving you an idea, the rack mount CDU rating is going up to 100 kilowatt. The standalone CDU rating is 800 kilowatt, while of course we also have to take into consideration working conditions. So we could bump it up to 1 megawatt if needed, but 800, 100, just keep that in mind. Last thing to mention, due to time constraints, it's also possible to have this CDU from liquid to air, meaning this is more for proof of concept or implementing those infrastructure into an air-cooled data center. Might not be the sustainable or the efficient way, but it allows to have a special area in a data center, air-cooled data center, with direct-to-chip cooled, higher dense cabinets. And then what happens is we transfer the heat out of the liquid loop back to an air loop and not back to a liquid facility loop. That's also possible. And again, here we have rack mount and standalone versions. Oh, yes, breakout. I didn't mention that we also manufacture PDUs. And you see this nice version on here with multi-ports outlets. We have the LED signaling on the screen, and we can also hot swap and turn around the controller, which makes it very simple to have one item for different requirements. But that was not the purpose I pulled it on. The purpose was just to give you an idea. Also, if we talk higher densities, we have to consider maybe different ways on how to distribute the power in the rack. Three-phase 32 amp versions are quite common. They give you 22 kVA. So to populate and power a rack with 80 kilowatt, you would already need 4 of those PDUs. Then you can move to three-phase 63 amp, which gives you a little bit more challenge because the PDU have a perforated chassis to have a little bit airflow, because we talk a lot of power here. But then even this, you would need 2 PDUs to power an 80 kilowatt rack. And this is without redundancy. So if you have an A and a B feed, you would just have to double the amount of PDUs. Just keep that in mind. Because here we got an example of a hybrid layout, and this is the combination of rear door, in row with the CDUs to cover the air. So this series loop within a rack is a nice feature, because here you take directly the return from the rear door, the preheated water into the CDU, you heat it further up, so you achieve a maximum delta T on the liquid side. But of course, it also works with additional pumps with a standalone rack mount CDU, and that's the example how it looks like. From outside, you don't see a difference, and I know I got a little bit beaten up because the picture is messy, but what I wanted to show here is you may also have to consider a rack design, because this is a cold plate cooled service, and you see there are 2 cold plates per rack unit. So we have a dual manifold in the rack, left and right, where we connect with quick connects the server. We have the data cabling that we have to clean up. We have the power cabling going to the PDUs. And as we implemented 80 kilowatts per rack, we have 4 times 63 amp three-phase PDUs. And the manifolds, this means this is quite a challenge. So what I'm still looking is getting the picture once it have been cleaned up, because of course this was during initial installation phase, but it gives you an idea what also comes to the rack design and what challenge could occur on that planning and outlaying design. And then last area, as we have heard before, and I would underline the same thing. Cold plate is really coming into play. We have a couple of installations now because it stays closer to the infrastructure that we know. Immersion, again, offers really going into liquid, everything into liquid, but it's the way what I mentioned at the very beginning, compute and cooling or infrastructure merged, because how does it work? We take a 19-inch server, we pull it in a 21-inch chassis, and then the cooling medium, the dielectric cooling medium, is spread it over the hottest parts and then returns to the rear side. So there is 2 redundant pumps and a heat exchanger. This means we are not flooding the complete chassis. It's only filled to 1/3. And that's why we have precision cooling, because we bring the liquid exactly to where it's needed. And then on the rear side, we have, again, a manifold. We connect the chassis to the manifold and we take out the heat from each chassis over the heat exchanger. And of course, you can scale this, and that's the main advantage. We stay in a standard rack design. We go in the height, so we can bring in much more computing power compared to a tank. It's easy to maintain because you pull out the drawer, you open it up, you work on your server, you pull it in again. And you can even scale it. So we can start with a small 1 rack-based CDU version or LTA version up to a fully populated data center in that space. And I'm just looking the timing. I think I'm already a little bit.
That's okay. Yeah, please push on. Thank you.
Yes. Okay. Yeah, I was thinking someone will pull a red card. Or everyone is dropping and just I'm talking on myself.
No, please take your time. Thank you.
Okay. No, I'm at the end. So the only thing I want to pull up is the last commercial, and then we get into questions. Yes, this is just an overview on data solution nVent. I like to pull it to the end because then we can really focus time-wise on the things that's really matters on the content. But needless to say, so we have all these products for white space moving into gray space, supporting the journey and the transition from traditional ways on cooling, power distribution, and racking into meeting this new or overcoming these new challenges. And then, of course, the last slide. If you want to learn more, there is the web link to our product portfolio offering and helpful resources like white paper and calculations tools that we offer. I think we have time for questions right now. Otherwise, again, stalk me on LinkedIn, Markus Gerber. I think you see my name here. Yes, just reach out whenever you want. Address questions, completely fine. And then, yes.
No, I just thank you very much. Yeah, and I really appreciate you trying to keep the time. I know it's really difficult, especially because you're running over, but thank you. And not a hint of nervousness could I detect at all. So, so I'm just going to jump quickly over to questions to finish up the day. So the first one we've had is, what is the redundancy options for your CDUs?
Okay, that's a challenging question. So the redundancy options on the CDU is we operate on dual pumps for sure, and it depends the version. Even we have an N+1 pump system, meaning 2 pumps operating, the 3rd pump in standby. There is no redundancy on the controller side. This means in that case you would really need the CDU's N+1. So you would have to add 1. So that's something we are looking case by case, and I should have mentioned that it's not just merging compute and server; it's also the standards are still lacking. So our CDUs are able at the moment to fulfill Tier 3. That's what we built in most cases. Tier 4 maybe needs a second look, let's say.
Thank you. And the next question, with the LTA version, does that mean an air-cooled data center can have liquid cooling without chillers?
Exactly. Yes, it's what we do. We take the heat out of the equipment and then we transfer it. So basically, we transfer it back to the air. as said, this is built to have a certain section in a data center to support this direct-to-chip or immersed cold servers. Of course, your air handling units need to be powerful enough, to get rid of the heat.
Yeah. Thank you. And then just one final question. Is Raychem part of nVent? I hope I've said that correctly, Raychem or Raychem.
Raychem, yes.
Thank you.
So Raychem, and let me get my friend from here. So Raychem and Caddy. Yes, Raychem leak detection and heat tracing systems are part of nVent. So we have close contacts.